Hello everyone, welcome on in. Happy Monday. We're going to be building a Python PyTorch transformer. We're going to be using the module that has been built into PyTorch directly. We won't be building our own custom transformer, though we might be doing that next. Today though, the plan is a very simple, just let's use the PyTorch transformer module that's built in. And I think that sounds like a good plan to me. I'm actually pretty excited about it. That's something that I've been wanting to do for quite some time now. And we might be able to get to part of it today. We might not do all of it today, but we might get through quite a bit of it. Let me do a quick little share of the link here really quick. And over to our Discord channel. Paste at everyone. There we go. All right. Let's get into building a transformer, which is, you know, the old important thing if you've been using the large language models to build anything or interact with ChatGPT. Hey, Bogey Ears, good to see you. Hello, sir. Welcome on in. Happy Monday. We're going to be doing some import torch here, and we're going to be using the transformer torch. And I don't know exactly how to do it, but we're going to figure it out. We're going to. Let's see. So we're going to be we've been building up to it. We built an embedding model, and we need to use an embedding in our training process. So I've got some things in my head about how it should work. I want to pull up the reference for PyTorch. All right, here we go. Transformer. Where is that here? I know it's around here somewhere. Let's see. I need to go to API reference. There, perfect. Transformer. Can we see it? Is it in here? How about in neural network? Here we go. Try this. Maybe it's in this. See, transform. Hey, there we go. That's what we're looking for. Oh, what? It's got an encoder and decoder right there? Wait. I was just going to do an embedding. Transformer encoder layer, decoder layer is made up of a self-attention multi-headed. Do we need to use both? No, I think we just use this. Okay. This is what we need to use. So we need to create a module, and then we instantiate this inside the module. And I think that should do the trick. I think that's all we need. Target, source, target, out. Okay, perfect. Okay. And it wants... Hold on. Wait a second. All right, so it's a 3D tensor. However, why are the source and target different? It's weird. It's weird, right? Isn't that weird? Recursion depth transformer. Ooh, hey, Bonzupi, good to see ya. Happy Monday. Recurrent depth transformer. Ah, yes. We're gonna do transformer today. We're just gonna use this right here. We're gonna try this. We're gonna learn how to use this, and we're going to see if we can make it work. We're just going to try it. It looks like it's pretty straightforward. However, I think we have to do a few extra things ahead of time. I can't spell. Hey, no worries. Looking at crash dumps all night. Hey, Kyle, you made it in. All right, Kyle, good to see you. Happy Monday. Sergio, good to see you. Welcome on in. Happy Monday as well. We're going to be building some transformers today. This is a very straightforward one. And then we need to figure out how to do a target mask, a source mask. I got to do both of them? A memory mask? Wait, what's going on here? There's a whole bunch of things that we got to do. I know we have to do the mask because that's going to help prevent leaking of information for the future, because you want to train the model, right? You don't want to give it any foresight. You got to take away the foresight so it figures out how to learn. Right, so yes, okay. We need to do some masking. I don't know how to do that. We're going to figure it out. I know we can do it. I know we can, because we are successful. We're always successful here. All right. So we've got a model which dimensions. All right. So this must be how many units there are per layer, something like that. We all wear masks, metaphorically speaking. Oh, Jim Carrey voice. Hey, Jim Carrey. I want to watch. I need to go back and see some. Hey, Torba. Hello, everyone. Torba. I was going to send you a DM. How was the tournament? You said 4 days, right? You said 4 days, so I didn't know if it was... That's not enough time yet, right? Hey, Loons, good to see you. How are you today? I'm doing good. We're doing good over here. It's the Ronin. Oh, it's the Ronin. Hey, thank you for clicking the hi button there. Good to see you. Happy Monday. We're going to be building Transformer today, you guys. We're turning to PyTorch. Yep, we're doing some PyTorch. We're going to be building a Transformer. We're just going to be using the Transformer module that's built in, right? The neural network module. Cool. Yeah, nice. Yeah, it was good. Had the last round today, and you traveled home. Oh, that's great to hear. Torva, did you win? Did you win? How good did you do? I hope you ranked really high. I really hope. I'm really excited for you. I was really excited because I did a lot of. The game that I played with you was the first game I played in about a year or so, and all the memories are coming back, and it made me really excited for what you were doing. Really excited. That's really neat. Sadly, it didn't make the cut. No, into the money. Got 3 out of 5. Oh no, 3.5 out of 5. Oh, Torva, no. There must be some really good players there, huh? You're launching CloudTube. All right, nice. Awkward without audio sub. Oh, whoops. How about that? Okay, now we're with the subtitle. Bogateer, thank you for. I'm like, whoops, I forgot to put those on. But hey, gained some LO. All right, good to hear it. Good to hear it. All right, now you've got the subtitles. They're back. They're back now. I just forgot to turn them on. Yeah. Thank you for reminding me. Now I'll feel better. Hey, all right, me too. Thank you so much. Attention's all you need. Yep, Soki, that's what we're doing. We got the Transformer. All your payment systems are connected to your old LLC. So I've been painstakingly switching to the new C Corp. Hey, Kyle, nice. Yeah, that's a lot of paperwork, right? You got to do some paperwork there. Attention's all you need, guys, right here. In fact, let's open that up. Let's see, where are we? Let's do the PDF viewer. And let's look at the attention equation. So when I saw this, I didn't know anything. I didn't know what was going on at all. I didn't know at all. Now I can walk through this. I know what the deal is. I know what's going on here. Mostly. I mostly know what's going on. So this part where it shoots on over upward, and then there's these outputs here, and then the output probabilities. So this part right here, I don't know what's going on right here. This is weird. Input embedding, output embedding, outputs. We don't have the outputs yet. We don't, or unless we have the target outputs. Let's see. All right, we had Transformers last week, but I must say, I didn't fully understand the attention mechanism. The attention part is actually the part I understand. I get that part because it's kind of like a correlation coefficient matrix where you just multiply all the values to each other. It's actually pretty straightforward. The attention mechanism we talked about. This is the attention mechanism right here. It's actually, I understand that part. It's hidden. It's not showing you what's going on because it's the QKV multiplied and softmax. And you do an add and norm. And then you do feed forward, which is... Wait, what? It's all feed forward. What do you mean feed forward? What's this right here? Does it mean a linear layer? Is that what that means? Add norm, another attention head, feed forward, and then a linear... Wait, what is feed forward in this diagram? Do you guys know? We're gonna find out. We're gonna look this up really quick. Hold on. Let's read this here. 1 second. All right. Let's go Gemini. Paste that in. What is the feed forward? I mean, what is that? Why is that? It looks like it's a thing, but the feed forward is just the process of putting data through the network. Loons is basically a neural network architecture that uses attention instead of recurrence. So it can process sequences way faster in parallel with the multiple heads. Yep, because you can slice, you can cut up that array and then distribute it and make it parallel. Gemini Cricket, yep, pretty much. Gemini Cricket, oh, Gemini, yes. Okay. You're talking about, I know what you're talking about. Disney, the Disney Cricket. Happy Monday, brother. Today's my birthday, Mark Gluman. Happy birthday. You did it. You went a year around the sun, a little bit longer. Hey, how's it going there, Conmore? Feed forward is 2 linear layers with 1 activation layer in between. That is the answer I was looking for. Conwar, thank you. Yes. All right. In the transformer architecture shown in the diagram, feed forward, yes, is position-wise fully connected sublayer. Yes, I understand that. Max. Really? We've got some weights plus bias times weight plus bias. So is this the activation? A max? Right there? Is that what that is? I'm confused. We're gonna find out though. We're gonna read it. We're gonna discover all the different things we need to here. Let's your conscious be your guide. Oh yes! Was that Pinocchio? Is that what that was? I'm just some dude who knows neural nets, and you're all trying to make sense of chaos. We're basically pattern matching machines. Wondering about pattern matching machines. They're just frozen numbers in time, you guys. Happy birthday, Mark. The activation layer is what provided the non-linearity. Got that part. We got that. Good to go there. Boketeers, let's say someone would like to train a large language model on cookbooks for recipes. How much training data would one be looking for? I understand the more the better, yes. But like where to start? Get all the cooking books. Get all the cookbooks, as many as you can. You probably only need 1, although it's going to be memorizing, right? It's going to be memorizing that one cookbook, so it won't be able to create the patterns it needs across all the cookbooks. Thank you for the hearts, you guys. Appreciate it. All right. So I get the add a norm. So we've got a norm layer. Feed forward. So this part I get. I understand this part. So you've got your inputs, which are your words. And then we convert those words into tokens, which is not shown here. They don't show that part. You convert them into tokens, and you throw them into an embedding layer. Thank you, brother. Nice. Let's say someone would like to... let's see here. How many AI subscriptions do you have, and at what tier? I know you have Gemini, Google Ultra. Oh wait. So you're asking me? Oh, sorry. Oh, thank you. Thank you for retyping, Loons. Thank you for retyping. I missed your message there. So I've got technically, I've got GPT. I've got Claude with Anthropic. So I've got OpenAI, Anthropic, and Google. That's it. Just those 3. Just 3. I got them, and I got as much as I want. All I can eat. It's almost like a spotlight moving across the context. Which part is? You have a Google and Claude? Nice. Yeah, Gemini is really good. With Gemini 3.5 Flash. Gemini 3.5 Flash is amazing. It's really good. I'm liking it a lot. All right, so I understand this part. So our input, we've got words, a whole bunch of words, just say like a book. And then we capture segments of that book into like a window. So we only have like 100 words, for example. Let's just say 100 words. Then we convert those words into tokens, which just means we convert them into a number, a positional number based on the dictionary. So the number between 0 and 100, which will give you the identity of the word itself. And then you throw that into an embedding, and the embedding needs to be the size, at least one of the dimensions needs to be the size of the number of words in your dictionary. Thank you for the 100s, guys. Appreciate it. Oh, Loons, thank you for putting that up. I'm going to pin your message there. Thank you, Loons. Yeah, Loons, thank you. Thank you. Okay. Now, then you have positional encoding, which is going to it's going to rotate based on the number. It's going to have a hard rotation on it. Okay, so there's an array that has a whole bunch of essentially, it's a circle. So it is a circle. And based on where the word is in its index, you're going to add, I believe it's just an addition, just a specific amount of numbers based on the because it's a full wave, right? It's a full wave up and down. So it's a circle. And that wave can be applied across your embedding output. And that just gives it positional knowledge based on where the word is. And then you do the correlation coefficient matrix attention. That part's straightforward. Did you see Discord? I put most of your free models. Yeah, I did. I added one. You're missing Gemma 4. You need Gemma 4 on there. Embedding is a mixed vocabulary size, time dimensions for embedding. Yeah, so embedding's actually pretty straightforward. It's basically a giant random linear layer, except for the feed forward. When you're doing the forward pass on an embedding, it's literally just a lookup of the row. So it's kind of like you've one hot your number, you multiply a matrix, and you just get back one of the rows. So it's really straightforward. It's actually really fast. It's a really fast one. And so that gives you the embedding. Exactly. Nice. Yes. See, we know what we're talking about here. We know what we're talking about. Then we've got the QKV layers, right? And you could have one large QKV, I believe, one large projection, as long as your QKV is the same size. If you have, say, different size QKVs, which I have no idea why you would ever have that. I really don't. I don't know why you'd have that. If you did, though, you could have separate ones, and I kind of want them separate anyway. I think it would be separate. There is Gemma 4 in the mess of the Cloudflare models. Oh, I missed it, really? I even searched, I downloaded the text file, and I did a text search for Gemma 4, and oh wait, you know what? I searched for Gemma, just Gemma, Gemma, and I only found 2 and 3. Isn't that kind of hard coding numbers? Is it? Yes, the positional encoding is hard coding because it is a fixed. It's just a wave that you apply addition based on the position of the token in your input sequence. I think these are hard coded here. For the multi-headed attention, you have 3 layers. They're linear layers. The QKV layer, and they're projections. Think of them like convolutional neural networks where you have filters. I would call that basically identical. Gemini is super weird about how you call models with APIs. It's weird. Is it? Is it weird? Have I ever called? The only ones I ever called were Anthropic and OpenAI. Those are the only ones I've called from the API directly. I've not called, I tried using the Vertex API when they first came out, and it was too new. It was broken, and I haven't gone back since. I have not gone back since. Then what is this add here? Why is it adding? Because we already did QKV. Do we have to add it back? So we just give a multi-attention, we add, and then normalize. So we just reposition all the numbers around 0. And then we do the same thing here. So we've got two linear layers here with 1 activation, probably ReLU, right? It's probably ReLU. And then we add again and we normalize. And then we do that a few more times. Boop, boop, boop. The part that I do not understand is this segment right here. What's this? I'm not used to this part. How do we know what the outputs? Shifted right outputs. Shifted right. I mean, our outputs, how far out is this going to be? Like, I don't know. I really don't. Hey, Cow Level, good to see you. Welcome on in. Fire hydrant. Wait, what about fire hydrant? How does companies afford to give out free inference? Loss leader. It's loss leader. Oh, it's one of my favorite terms in business. Loss leader. Have you guys heard about this? It's where you create something that is attractive and will get you customers, and you give it away for free. It's a way to attract and retain customers. You want some loss leader, and then you get portions or a conversion off of that audience that you've generated to become paying customers. It's my favorite. I love it. I love Loss Leader. It's so good. Add is for adding residual. Add. I suppose I understand this part a little bit because I can see where the arrows are coming from. So I visualize the inputs here. So you've got the original value. You split that value 4 ways. You do query, key, and value, right? QKV. And this goes through 3 filters. You could do it through one big one, but I'm going to say there's 3. And then you do softmax and you do some multiplication for correlation coefficient. And then you do another multiplication and you're good to go. Pubnam's free plan is a loss leader. Exactly, Bonzupi, you know it. You know it, Bonzupi. Mask body head attention is where token only attends to everything before and not things that occur after the token in sequence. Let me say that again. Masked multi-head attention is where token only attends mask. So right here, I understand the mask part because I know what a mask is. You have a number, basically 1 or 0 or fraction thereof. You could like blur out some things. And it's typically at a diagonal. So you're going to have a whole bunch of ones in the top corner, the top right corner of your square, and all the zeros in the bottom right. Bottom left. Notice, hey, Peter Parkour! Most models are tightening token usage limits. Tokens gone. Oh, the good. Yep, the standard of the future. You got it. Hey, Trevor, how's it going? My profile picture is me. Oh, it is. Trevor, let me zoom in on you so I can see you better. All right. Yep. We've got her. So my profile picture is me too. All right. You can see there. We got Trevor, you guys. Actual profile picture. All right, let's zoom here. All right. I've got a poll for you guys. How many transformers, you guys? How many AI LLMs are you paying for? All right, I'm curious. Let's see, because that was Loon's question. Loon asked me that. So 1, 2, 3, and 4 plus. There's probably going to be no 4 pluses in here. If there are, what are you doing? What are you doing? My profile is C. Yeah, it's C. It sure is. Yes, blurring those out things allow token to only look at anything on the left and not the right sequence. Got it. Got it. All right. So I understand this for the most part. I get the QKV part. Here we go. All right. Scale dot product attention. QKV. Right here, we do a mat mult after the softmax. And QKV are the same. Just to let you guys know, QKV, they are identical. They are identical. Although, are these the linear layers? The filters? Are these oh, they are. They are linear right here. Query key and value, linear. Scale dot product attention, right? I knew it. All right, so these are the filters right here. Like in a convolutional neural network, you have a filter. These are essentially projections. I'm not paying for AI. Bonzupi, very nice. Very nice. You're getting away. Hey, bro, what's going on here? Oh, Sai, how's it going there, Sai? We are doing Transformer. We're doing Transformer. We're walking through the algorithm, which to me, I'm like 90% understanding. I mostly got it all. I get every piece. I understand this part. Concatenate, and then scaled dot product attention, concatenate, and then throw through a linear layer. Multi-headed attention. Shouldn't it be 3 plus and none? Oh, right! I didn't even think of that, Loons. I should have done none. I didn't even think. I guess you have to abstain from voting if you haven't paid for one. Query key and value are all the same, but they are projected by different weights. Yes. So Q, K, and V are all the same. These are identical at this point. The linear layers are random weights in each one. They're like projections. You pass that through and you do the scale dot product attention, which is this algorithm here. Really straightforward. Matrix multiplication between query and key. You scale it, you mask it optionally, you do softmax, and then you mat mult again with the same value. And therein lies... That's so neat. Oh, we could build that right now, couldn't we? Can you show my picture to everyone? Can you show my picture? Sure. I so. Here you go. I'm zooming it. That's as far as it zooms in. And you got Trevor, Bonzupi, Bogateers. NVIDIA NIM is enough. Wait, let me see here. Oh, what? Whoa, whoa. That's weird. That's very odd. Why is it doing that? That's very odd. All right. Let me zoom back out here. Here we go. There we go. Okay. What are you saying over there? NVIDIA NIM is not enough for you to be honest? Oh, it isn't? I have not tried it. I've not tried it. Let's focus on Transformers. Peter Parkour. Yeah, let's do it. She sent a different diagram in Discord General. That's cool to take a look at. All right. I want to take a look. Yeah. Grok Cloud free. Gemini free. There you go, Cal Level. There you go. All right. So I do have a... So I think we have to do... let's see. Class. We call her our transformer. Torch.module. Init. Let me see. Def. Init. We do super init. All right, there's a little bit of code. All right, that's 2 seconds of code. Sure to slow. TT, wait, what is that? Open Router got some really good free models. Oh, Loons, nice. I didn't know about that. You're on the Nun subscription. Gemini education count. $1 in. Yep, there you go. It's costly, isn't it? It sure is. Hey, the F4, and good to see you. Welcome on in. Happy Monday. Have you hung out in the IRC the old days? Oh, I remember. Is nn.module? I think not torch.module. Thank you. Good memory. Good memory. Here, let's do this. Python transformer. Did I not save this? All right. Oh, it's the wrong directory. CD // transform desktop transformer. There we go. All right, Python transformer. All right, it should just run and not crash. Perfect, okay. Haven't seen the / emoji where it's like, hey, you're waving. It's like, how's it going, everyone? In ages, right, Bonzupi? The old IRC days. Thank you, Conwar, appreciate it. Takes 39 free modules list. Wait, NIM takes 39 lines in your free modules list? Gemini or Claude, which do you prefer? It's Gemini's got really good mark limit. So mostly Claude. And then Gemini for the 3.5 flash. 3.5 flash. I like that one a lot. The URL is buildnvidia.com, not like nimnvidia.com. It's weird. It's different. It's different. Here's a different diagram. Oh, thank you, Kyle. Thank you. All right, let's look through this diagram real quick, you guys. Ooh, it's going to give us a walkthrough. Ah, here we go. All right. So here's your input. Oh, wait. Oh, it's missing pieces. It's missing pieces, you guys. Where's the embedding? It's missing some steps. Whoa, transformer block 2. So you just stack the transformers. Is that what you're doing? Connect with you next on stream. Your stream is very engaging. Oh, Conwar, thank you so much. Appreciate it. It's good to have you here. 3.0 Flash is pretty good. Got a little bit of usage for free over the Google API. Nice. You wanted to read that? Wait, which part? Here, let's go back to the beginning. All right. So this is missing pieces. Oh, wait, see right here, the embedding. There we go. I was like, where's it doing the thing? It's wrong. All right. So you've got your words. Data visualization empowers users to, and this must be some sort of empowers. All right. Thank you for the hearts, you guys. Appreciate it. Thank you for the party poppers. We tokenize it, which basically assigns a number to your word. That's what that is. That's what tokenize means. And then embedding is an extra step. So they're merging these two steps here. So this is wrong. It's missing a step. This is not including the embedding layer. Please explain. I didn't really understand it. All right. Thank you for the hearts, you guys. All right, so when we're building a large language model, we start with the attention mechanism, right? We want to add that attention mechanism, which is, I call it a built-in correlation coefficient directly into your AI model. Basically, it's just self-attention where you multiply the words by each other. Every word gets multiplied with every other word. I know, it's like, wait a second, that sounds simple. It is, it really is. Where's that ChatGPT gets obsession with the M dash, isn't it? It gets very obsessed with the M dash. Is that the M right there? That could be visualization powers. It might be an M dash. It's hard-coded into the training scripts. There's a lot of it. Hey, how's it going there? Divyanshu, thank you for joining. I appreciate it. Join the right channel for software engineering. We're currently doing a lot of focus on AI. And today we are going to be investigating and typing up some code to do a transformer. We could write our very own from scratch, which we are planning to do next. We're just going to start at the top level of transformers, and we're going to get something that works using the built-in transformer class that already exists in PyTorch. So we will be walking through this. That's where GPT. So have you talked about how the agent could just talk with tokens yet? Oh, right, Kyle. That was your idea. That was your idea that you had maybe for the hackathon, right? For the blocks hackathon. Yes. And so instead of doing this tokenization, you don't need, if you want the AIs to speak with themselves, you don't need to translate to English. There's no need to translate to English. Hey, how's it going there, Jinya? Good to see you, Jinya. Nice to see you too. Good to have you here. Oh, Abhishek. Hey, Abhishek, good to see you. What's up, bro? How are you? Doing very good, thank you. We're doing transformers today. So every token, every word, and every token is hard-coded to a word. Yes, that's it. All right, so the word data will get translated into the number index 6601. Now, it doesn't really matter what the number is. It's just whatever's in your dictionary. So this is missing a step here as well. It's missing a step. The ID will then be passed through an embedding layer, which is just another matrix. It's a multi-dimensional matrix with one of the dimensions equal to the number of words in your dictionary. Your dictionary is going to be what your model learns on. So if you have like 100 words in your dictionary, you'll have a number that corresponds to that word between 0 and 100, right? Well, 0 to 99, or if you want to do that way. It wasn't your idea? Well, you just shared the idea. It still sounds like a good idea though. It was your idea to share it. Hey, right? Otherwise I wouldn't even have heard about it. Good to have you guys here. All right. So very simple, convert the word into a number, the ID associated in your dictionary. You generate your dictionary by taking all your possible words, finding all the unique instances of those words, and then putting them into a list. You have a giant list of words now. And all those words have a number between 0 and 100 or however many words you have in your list. Then you have an embedding layer, which is a two-dimensional matrix, and you grab just one of the columns or rows. It doesn't matter how you look at it, a column or row associated with the ID. And it gives you a whole bunch of numbers. And they're randomized at this point because they're not trained yet. Fair enough? Yeah, it counts, it counts. Once you have the embedding, which is just one of the rows from a matrix, a random number matrix, then you do positional encoding, which is a bunch of waves in a fixed wave, right? And so for every token that you have, every token embedding parameter that you have, all the embedding parameters will get added to this wave. Very simply, that gives you your input. We only just got started. We're at the very beginning. We're at the very beginning of the transformer, you guys. It hasn't even gone further yet. Now that we've got our words, they're embedded and positionally encoded, which is great. The positional encoding is fantastic because it allows your correlation coefficient matrix, which we're going to be doing here in the future, to self-attend in a way that can detect where a word's position is throughout the sentence. And it can have a different meaning. It allows you to assign a different meaning based on the position of the word. Hey, Nick Steffen, thank you for subscribing. Appreciate it. Good to have you here. We're going to be talking about transformers today, you guys. Kyle, thank you for sharing this. This diagram is fantastic. Okay. So now that we've got all of our embedding and all of our numbers positionally encoded, we've got a dedicated vector, which is a one-dimensional array of numbers around between 0 and 1, give or take. So now we've got some numbers for every word. So we've got essentially a giant matrix here representing a sentence. Do you like rock music? Hey, JJ the artist. Hey, JJ the artist. Good to have you here. I like some rock music. Haydar, good to see you. Welcome on in. Happy Monday. Good to have you here. We're going through some transformers, you guys. Now we've got the QKV. Now, QKV, these are linear layers, another matrix now, randomly initialized to random numbers. So we've got yet another matrix, and each is different. So the QKV are separate matrices. When we pass through these filters, or you can see them as projections, we do a matrix multiplication with our input data. So for all of our input data. Let's see if this gives us, what does this look like here? Okay. So here is a representation of that. Key, query, and value. One thing that I think is very important to note here is that this data rate, all this data is identical. These inputs here are the same. All the same right here, right? So data visualization empowers users to, data and visualization empowers users to, and then it's the same. So it's all the same. So this is where the self-attention comes in. It's going to be really silly when you hear about it. It's going to be so silly. When I saw this, I'm like, wait a second. Is that what self-attention means? It sounds so powerful. It does, doesn't it? Doesn't it? Self-attention seem amazing. It's really just multiplying every word with every other word. So it's just a correlation coefficient matrix. Basically, you take all these numbers and multiplying with each other. So data gets multiplied with data. Visualization gets multiplied with data. M gets multiplied with data. So it's just a full multiplication adventure here. Right? So everything gets multiplied with themselves. And then you could do a mask, which is going to deactivate the top right corner of the square. Basically hides the top right corner of the square. Mostly because when you do that, these are uniform matrices, and so you don't really need the top right corner of the square anyway. You're not losing anything. The input box at the top, it uses GPT-2 and predict the next words. It's so cool, is it? I kind of think it's pretty neat. Vector multiplication, basically. Exactly! It's vector multiplication! Matrix multiplication. I didn't finish Calc 3. Hey, don't worry. It's just put numbers, mushing the numbers together. That's all it is. It really is. We're going to put this number with these and push them together. That's what AI is. It really is. It shows the process in real time. Yeah, try it. All right. So you said here it does? Let's see. How do we, what do you mean? I'm clicking on things. I like this part, right? Query, right? Dot product, Q times K transposed, which is standard matrix multiplication. Scaling, which means that we are going to add some sort of M, which is mask. And usually a mask is multiplied. I don't think it's added, so that sounds like a mistake right there, right? This M is a mistake, right? That plus symbol, it should be a multiplication symbol for the mask. At the top, okay. Examples. Generate temperature, multi-head, transformer. Let's see, I'm clicking on buttons. I'm trying to figure out where it is. MLP, Multi-layer perceptron, right? We're not there yet. Probabilities. No, that's the output. We don't care. That's like the very end. The generate button. Oh, let's try it. Oh, look at that. Hey, all right, loons. All right, I didn't see how the generate button works. Let's try it again. Ooh, very nice. Try it again. See how it works there? And just to let you know, these are all a bunch of numbers, guys. It looks complicated. It's really just a bunch of numbers. That is pretty nice. You can have multiple heads, which is the same thing. And the multiple heads doesn't really provide any benefit other than my understanding is that it makes it faster. So it's basically you're splitting the vectors so that way they can operate simultaneously across multiple cores. So that part's the fast part. So in the end, AI is just numbers. Yeah, it is. Exactly. It is. We feed it words. The AI kind of says, I want numbers. Does its thing and then translates it back to us. That's it. You got it. You got the encoder and decoder. That's it. You figured it out. Hey, Driven Zero. Love your consistency, man. Hey, thank you. Good to have you. Welcome on in. So you're reading documentation and building things. Yes, that's exactly what we're doing. We're going to go through the full transformer. I've done this. I've gone through transformer. I've built my own and I've created some videos 2 years ago now. And I'm going to do it again, but this time in PyTorch. Bros, good to see ya. Welcome on in. Happy Monday. Gotta go to. All right, sounds good, loons. So more layers, more accuracy. More layers, more accuracy, and be careful. Gradient vanishing. Gradient. If you have too many layers, your gradients can vanish because they start. Then it just diminishes as you do back propagation, and you're creating more gradients. The more layers you have, numbers get tinier, 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 smaller, smaller, smaller. So it makes it difficult to do optimization if you have too many layers. We need to solve that. RailU solved that a little bit. However, you still have deactivation and a major loss of data as you add more layers. Even with RailU, you guys, even with RailU. What time you come live and how often? Every day, Driven. Every day around like between 10 and around 10 a.m. Pacific. Daylight time, United States, Seattle, Washington. The Gradient Vanish is the title of your next EDM song. Hey, that would be a good one. You could do it. You could do that. That'd be great. All right. Oh, I clicked generate too many times. It gave up on me. It sure did. It's like, no, you can't have any more generations. All right. So the attention mechanism, pretty straightforward. You do your matrix multiplications, which is dot product, query times key transposed, scaling. I think this is wrong. The M should be multiplied, not added, right? Because you're basically deactivating the top right corner of your matrix. And then you scale it with D, which number of dimensions, times K, which I'm not sure what the K is here. You're basically shrinking. You're shrinking it, so it makes it a little bit less intense. A smidgen less intense. Every model works on different numbers, right? Like still the same, but the numbers mean something different for every model. Yeah, they do. They sure do. It's organic. I'm thinking of starting your IT career in web development. Hey, how would you rate the Odin project? Will it give me the skills of getting hired? Oh, I don't know. CNOS? What is the Odin project? Odin. What is this Odin project? What is it? The Odin project. Your career in web development starts here. Our full stack curriculum is a free and supported by passionate open source community. I've never seen this. Intermediate, advanced databases, React. It's full stack. Look at that. Explore the curriculum. Full stack, explore. Ruby isn't necessarily today. You're going to be mostly using Node.js probably. So do they have a non-Ruby? Let's see, JavaScript Advanced React. Here we go. Node.js. There we go. Open the course. Introduction. All right. It looks pretty good to me. Hey, Sai. Hello. Welcome on in. Good to have you here. What decides which words are the key words and the weights? It's all based on the model. So the model makes that decision. Where are we? Here we go. So right here. This is just the algorithm. So you multiply every word with every other word, right? You multiply all the words with all the other words, right? So simple multiplication here. There we go. The center always is the same word multiplied with itself. So you see data, is, being, and used, right? And the top right will be the data. This is the input. Hold on one second. All right, that's music. All right, I just had to change up the music there for a second. Is this part of the math you don't... Oh, wait. So this part is where the math gets multidimensional. Yeah, does it? Let me see. So it's already multidimensional-ish. So let's see here. It does get multidimensional when you get into the embedding layer, because it's going to give you a vector per word, and then you've got a 2D matrix at that point, right? You got a 2D matrix. Then you add your position encodings to... Then, for each vector, each word is a vector, you multiply that. And then you apply a mask. Boop, 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 boop. Swoop. Right? And then you do a softmax on it, which is going to scale all the numbers from up. So 1.0, does it usually go, does it scale? Oh, right. Usually a softmax is, so this might be a bug in their diagram. A softmax will give you all the numbers combined will add up to 1. Right? All numbers add up to 1. I believe, right? Let's double check that. Jiminy, let's see. Softmax, all values add to 1. Let's see if that happens. I'm pretty sure that's the case, right? Yes. That's the definition, the defining property of softmax function. So they do have a bug here. This is a bug right there. We found the bug right there. It's a good diagram though. It's a really good diagram. Yeah. AIs are kind of WYSIWYG. Imagine funding that is at scale, at this scale, and then realizing you don't know how to adjust it. That's a good... Yeah, that's fair. That's fair. I'm with you on that. Hello. Peace, Lord. Welcome on in. Happy Monday. We're going through transformers, you guys. We're going to walk through all the different parts of the transformer so we have an understanding of it. And then we're going to start typing some code here that uses the PyTorch transformer. 0, I use free buff. Hey, I should have done that. All right, here. Let's see. All right, let's do a new poll. All right, in poll. All right, quick fixer. Let's do a new one. All right, so do you pay for AI LLM / code generation? All right. Yes, no, a lot. All right. New poll, you guys. So see, happy Monday. I'll try to ask them about the bug. Yeah, all right, yeah, definitely. So it's not like it's a big bug. It's not a problem. It's definitely broken because softmax is supposed to return a number collectively across the entire matrix. Should be a number between 0 and 1 for each of the cells, right? And the problem that I'm seeing is that we're getting numbers that add up above 1. So that's the bug right here. From a visual perspective, it's actually fair because you're seeing the whole point of softmax is to identify the strongest signals. It's no add, but DE. Wait, quick fix? Quick fix? What do you mean? Maybe we'll get some crazy edge case response. Maybe? I don't know. We'll find out. Softmax for converting into probability ranges from 0 to 1. Yes, they are probability ranges. The challenge is defining property of the softmax function takes a vector of arbitrary real numbers and transforms them into a probability distribution, like you said. Every value of the output falls between 0 and 1. And the sum, this is the key part right here that's broken in the diagram that we've been showing. The sum of all output values is exactly 1. Right? And if we look at this, we see cells here that exceed that. So these cells right here, they go above 1. So that's the broken part. That's the broken part. You didn't finish your sentence? Free buff is kinda overkill. What is free buff? I'm not familiar with it. Peace. Peace, Lord. Nice. Let's see. What is free buff? Okay. Now that we've done our attention and we've merged everything, let's see. There's parts missing as well. So we do have the feed forward, which is fine, the MLP. This is a standard. Multi-layer perceptron is just a bunch of dense layers. A bunch of more matrices. They're all matrices. Everywhere you see, there's a matrix. Don't worry. If you don't see a matrix here, there's going to be a matrix. And there is an activation. And so they're using GELU, which I like GELU. I like me some GELU. AI agent free, no subscription. Oh, and no advertisement either. What? Quick fix. All right. We learned something new. We learned something new. All right, the MLP is easy. That is just a bunch of linear layers with matrix multiplication and activations. We get that part. What is 11 more identical transformer blocks? So you stack the transformer. So it's a bunch of stacks. So what you see right here, this transformer block, we see a whole bunch of them, right? It just keeps on stacking over and over and over. Although the words at this point are not the words anymore. They're no longer the words. They're not. Although, if this is a separate head, then it is because it's just a segment of the word, right? So if this is the multi-headed part, what we've done is we've taken our input embeddings and we've sliced them. We sliced them out. Hey, Peter Slow, welcome on in. Good to see ya. Happy Monday. Show us more. We're gonna see it. We're gonna see it. It does use ads. I mean, I don't advertise it. Oh, quick fix. Got it. Quick fix. Okay. So it's free. And you can use it. It just has advertisements. Got it. It's minimal. It's CLI. Does not block the CLI. All right. Good to hear. Good to hear. So we continue to pass forward multiple segments. Multi-headed attention. Wait, hold on a second. Where's that? Residual? What's this? What's residual? I'm not familiar with that. I don't know what that is. 2 more identical transformer blocks. Okay. Let's keep going. All right. So that's a lot. That's it? That's all that does? Okay. Wait. I don't know why it's 12. It doesn't have to be 12. Love you, man. Peter Slow. Thank you. You know, it's a holiday, right? I do know. We're streaming anyway. Happy Labor. Wait, is it? Wait, no, not Labor. Memorial Day. It's Memorial Day. I almost mixed that up. That ad, right? The ad? Yeah, I believe. Do they add? I think they add. They might add. They add or stack. One of the two. Add or stack. Because if it's the multi-headed attention part, that just means that you've split the matrix into 12 matrices. And then what you can do is you can split that work across multiple cores. So that way, when you're computing the attention, you can do it quickly. It's like a fast attention. Try it once. Use an alternative to codecs. Love your videos. Hey, all right. Sounds good. We'll have to give it a shot. When gonna do back propagation? Oh, yeah, that's right. Good question. So this is just the feed forward part. We haven't even gotten to back propagation yet. Although basically all you're seeing right here, this everything just gets unwound in reverse. So that's the full backpropagation part. So you get a lot of backpropagation there. So then we get the MLP. Then we got residual, which I don't know what that is. However, after that, we're going to... oh, you're from Turkey. I'm from United States, Seattle, Washington, you guys. Where are you tuning DSP? What is... Oh, wait, Vishwana, what is DSP? It sounds like something I should know. Data system something. I feel like I should know what that acronym is. New York in North Bay Area, California. Hey, yes! Netherlands. Nice, you guys. Digital signal processor. Oh, see, I should have known. I should have known. It's not a common acronym in my day-to-day. However, I do know what that is. What makes the difference between DeepSeek 4, Flash, and Pro version? Smaller. Smaller. Fewer weights, which means it has fewer knowledge and fewer nuances. So the Flash is going to be smaller, have less resolution, and it won't be able to remember all the finer details of the nuances. So it won't be able to perform as well. It still performs well, just not as well. Digital signal processor for car audio. Oh, DSP for car audio. To make those, to change the wave patterns. Got the parameters. Okay, so now we've got our output. Scaled. So you do a scale, right? Which is going to convert all of your outputs, which can be pretty big numbers here. And then you scale them. Looks like it's normalization. Interesting. And then you do a top K, which is going to give you, it's going to sort for the top winners. The top candidate winners. What does that mean? What is the possible next word? Right? So these are our tokens. And then you see the probability distribution across these top K. And you softmax the output on these. And you ignore everything else. Interesting. That's a step that I'd not ever thought about. You don't have to do it that way, but that actually works. Implement a codec. Usually, it's a massive digital analog converter, basically, Peter Slow, or it can be a digital modem. I know what the DACs are. I remember the DACs. DAC. More powerful ones implement video codecs like H.264 or 265. Hey. A tip, if anyone watching, turn up your resolution. Oh, right. Yeah. Sorry, I should have zoomed in for y'all. So if you get your logits, which are your output targets, scale the logits, which you don't necessarily need to do. You just need to get the top K, and then you softmax those. And you don't necessarily have to softmax them either. Only during training. Softmax is only necessary here for training. Because you need... Hey, Steve. Hey, how's it going there? Bad Redden. Hey, Steve, thank you for saying hi. Good to have you here. Happy Monday. This website you're showing us, this is a website. Yes. This is Kyle. Flip with Kyle shared the link for us. Let's see. Residual connection. Transformers have an auxiliary feature that enhances the model's performance. For example, a residual connection adds layers input to its output, keeping information from fading through many blocks. In GPT-2, it's used twice per block to train deeper stacks effectively. Interesting. Okay. Layer normalization helps stabilize both training and inference by adjusting the input parameters so their mean and variance stay consistent. Normalization is just going to reshift the numbers. So the numbers might accumulate and get big. So like you've got a line, a number of line. So let's see here. So let's say we've got a number line here, right? And your numbers, you'll start out here. So you've got 0, and then you've got 1, 1.0, and you might have like a -1 over here, right? And so it's possible that all of your values will show up here, and they're going to get bigger and bigger, and they might exceed that number. So you get more values up here. Basically, what you're going to do is you're going to grab all these numbers and you're going to shift them so they center on 0. And that's a normalization trick. Come on, get all the numbers. Here we go. Number. Oh, come on. I can do computer, I swear. All right, here, okay. So we're gonna move all the numbers and reposition them to 0, like that. So that way everything scales and it doesn't get too big. So it's just a normalization. Easy, that's what that is. That's a simple, easy step. Followed by dropout. Okay, dropout is pretty easy, adds a probability that each number that's being performed math on, whether you're doing an addition or a multiplication, has a chance of returning 0. That's what dropout is. Dropout randomly turns off some connections between numbers so the model doesn't overfit to specific patterns. Yes, because you could have a bunch of patterns that are very common, and it makes your model perform really well for those patterns and really terribly for patterns that it is not very common, right? So if you have uncommon patterns, this helps resurface those uncommon patterns. I can do computer. You sure can. I'm trying to, but I don't see the website link. Oh, here, here, the website link. I'll put it under Discord, you guys. So under link share. Thank you, Kyle. Kyle also put it in the general, I believe. Here, yeah, it's also here. There we go. So we just went through the entire transformer. We did. We went through the whole thing. It's actually pretty straightforward, right? It's pretty straightforward. A bunch of numbers is what it is. I guess I should go to join Discord. Hey, there you go. Shall search the portion of the screenshot I just took. You could do that too. Yeah. Discord is the place that we post all the links. It's better on Discord because everyone can share links there. Because on YouTube, it doesn't let you share links unless you're like an Uber mod. And with Discord, all the links are shareable there. Everyone can share a link, and the links stay around even after the stream is over. That's one hell of a sheet. Very nice done. Whoever did it, so informative. It's great. It's actually really nice. It's really nice. There's a lot of steps here. Let's go through this one more time. The architecture behind modern AI powering models like ChatGPT, Gemini, introduced in 2017 by Google. Attention's all you need. Same architecture used for training a massive data set for inference to generate outputs. Here we use GPT-2 small, simple, and perfect for learning the fundamentals. Transformers aren't magic, but they build step by step. Let's see here. What is the most probable next word that will follow this input? That's it. That's all it was. If you thought it was something different. YouTube. Embedding, transformer block, and probabilities. That's it. 3 main parts. You got your embedding in tokenizer, embedding, positional encoding, transformer block with self-attention, and probabilities as the output. All right, Steven, thank you for the heart, Peter Slow. Steven, what is your best estimation on how much math is needed when doing AI and related field? So I hear a lot of scientists will have invested a large bunch of their time in math. And they all, of course, are going to say it's worth your time to do the math. Not just worth it, it's mandatory. And if you don't know the math, you'll never learn anything for your entire life. You know what? I think they're wrong. They're wrong. The math, yeah, it can help. You don't need it as much. I don't think you need it. It helps. Don't get me wrong. You're like, whoa. I've been studying math for many years and I need it. It's not necessary. I think if you're just going from the coding side of things, it will become apparent what happens required to build step by step. All of the math can be secondary. I don't think you necessarily need it. You need a little bit of math, probably like multiplication, addition, subtraction, like, you know, the basics. The rest, all these transformers, all these AI models, that's all they are. It's basically a combination of addition, division, multiplication. Maybe a few other things in there. That's it. That's it. You don't need to study heavy math to be an AI scientist. You just don't. I know you might be like, hey, I think you do. Nope, just kidding. You sure don't. All right, and if you're curious about the temperature, you guys, it's actually pretty straightforward. It's going to give a random probability on what word is being selected. So if you have a high temperature, you get a high chance that the distribution of the probability of words being selected in the top K will be different. Remember one thing from school. One time, my Latin teacher asked why her camera software didn't work. For context, it's a web app. And the fix was to allow the web app to access the camera. Yes, the pop-up and says, would you like to allow your camera to be accessed by the page? Loons, that's funny. Many roads lead to Rome. Some walk with the coding, some with mathematics. Yep, you're right, Bogateers, you got it. What? No linear algebra? I can understand anything. You sure could. You can start with the code. You can start with the math. I think all roads lead to Rome. Many roads lead to Rome. And to me, Rome is the code. Because you can do this in math on paper. It's not going to get you anywhere, though. Because computers need to compute this. So you need the code. You got to have it. So whether you start with math or start with code, you're going to end up with code. Right? Math is the base of every new tech. Math is the greatest of all time. She isn't that tech literate, but that is a level I can't describe. I know. All you need is to stick with environments where math is explained well. Hey, cow level, that's a great way to put it, right? It's a great way to put it. I like it. I like it. Math literally is everything. Without it, you're just moving pixels around, hoping something works. Hey, that works too! You can just move pixels around. It'll work eventually. You can make it work. All right. So now that we've gone through this, and you realize how simple it is, it seems really simple, we can get started on our Transformer class. All right, let's copy this. All right, so we're going to need a few things here. We need to do our dictionary. We need to tokenizer. We need our embedding. It's basically our encoding, decoding. Right? Encoder, decoder. For 2 embedding layers. Then we need our transformer layer, transformer, which is going to be self-attention. It's going to add multi-heads, which is going to allow us to parallelize it. That's all that was, right? Sometimes if you just know the concept of the math, you're good. Sergio, it does help. Because then you have that foundation and you know what the output and the inputs need to be. So it does help. And don't get me wrong, you're right, it does help. But to render those pixels, you need math. Even basic rasterization is just linear algebra, translating 3D coordinates to a 2D pixel on your screen. Yep, 2D pixels on your screen. Math is this, that. Math, this, that. God, mathing this, that. You just created a function. All right, so transformer, self-attention, multi-heads. And then we need the linear out for our target token output size. Basically converter. This is the converter. So you need a converter to embedding. I don't remember this part as well. Do we need to embed it, or we just get is it just logits? So we need multiple embeddings, right? Not just one. So here's the first embedding, but we need a final embedding. We need the output embedding. Scale top K tokens. Yeah, so here's our tokens on the possible output. Do they need to be... I think... we'll figure it out. Hey, hello. Good to see you. Welcome on in. Good to have you here. Thank you for saying hi. What's an embedding model? So an embedding is a matrix. It's really simple. It's just a matrix. And let's jump back over here. So embedding. All right. So this doesn't visualize it very well. Here, let's see if Gemini can visualize it. Gemini. All right, maybe visualize the matrix of an embedding layer. It's just a 2D matrix. So imagine a 2D matrix, a spreadsheet. Imagine a spreadsheet. Here we go. It's a spreadsheet. That's the embedding. It's just a spreadsheet. It's all numbers, you guys. It's all numbers. Turn words into data and vectors so machines can actually work with them instead of just text strings. Yes. So it converts words. Sort of. There's a few steps. What are you making today? We are building a transformer. So we're going to be using the native PyTorch transformer class to get started. Then after we get that working, we're going to train it a little bit and create ourselves a little, maybe a small language model, right? After that, we're going to build our own. So this is a built-in class right here that comes with PyTorch, pre-built. Later this week, we'll be building our own transformer from scratch. Let's roll, Steven. Love the welcome of Gemini. Yeah, exactly. It's really good. It's not a digital savior or magic genie. It's a spreadsheet, guys. Hey, Kyle, exactly. You know it, Kyle. So each token is basically a word. Just think of it as a word. You can do it differently if you want. There's something called byte pair encoding that splits words up into like components. So you could say the word EM is a word, bed is another word, and ding could be another word, right? You could byte pair encode it. You don't have to do that. You don't have to. You could just do full words. So you've got your token. Each token is a word. And what's missing here, it does say one hot vector multiplication. You don't have to do multiplication. You just grab the row that's associated with your word. And that will be the embedding value. Then you can create a matrix from that. Make it real easy. You guys. Squagletto. Hey, what? What do you mean? Squagletto. What is that? I don't know what you're saying over there. So yeah, this is what an embedding looks like, you guys. Each word gets its own set of numbers, right? And you get, yep, there we go. Vector for the word the, for cat, and padding is usually the first element in your embedding because it starts with 0. The cat matrix. There you go. A bunch of words, you guys. That's what that is. How many bytes is a token? It depends on your dimension. So if you want, you can make it one-dimensional. So your token might only be one number. You can do that. You can. You could do it if you wanted to. It's up to you. And the more dimensions you have, it's actually pretty valuable because it's going to give you... Well, let me think about that for a second. When you're doing back propagation and you're converging and you're training your model, your embedding layer waits update as well as it learns. So some words are similar, right? Or they're like similes. They have synonyms. These words will start converging on their numbers. So if you don't have enough dimensionality, you won't be able to represent the distinction and the synonyms. So it's important to have enough. So usually you can get away with something like 128 numbers per token. Will you make stimming or lemonade? Yes! You've done this before! Yay! Look at that! You know what you're talking about! Yes, I like doing that approach because it went in text. Look, see all the text here is like the mechanics, one hot vector multiplication. All the words are capitalized, so you can reduce the capitalization. You can reduce the number of tokens by going to lowercase. Then you can do stemming, which removes like the INGs, right? You can remove the INGs, right? So it's just embed. So you can stem the words, right? Lemmatization is another similar approach. Let me see what lemmatization is real quick. Lemmatization. Wait, that's what I thought stemming was. wait. I thought that's what stemming was. So you see how you've got ING and ED and E. Lemmatization is a text pre-processing technique for NLP that reduces inflected words in a valid dictionary-based form known as lemma. It accounts for grammatical context as part of speech, converting variations, running to ran. So you could do that. Oh, okay, yeah. So running becomes run, studies becomes study, better becomes good. So yeah, it allows you to reduce the number of tokens. Your dictionary size can be reduced. So it varies per token. Yeah. Every token is going to have a different number set. However, each token will have a uniform number of numbers. They will all have the same number of numbers. So the word the will still have, like, for example, 3 here. It'll still have 3 numbers. Let's say the word cat, it also has 3 numbers. Same for the word matrix. It also has 3 numbers or more, right? More for it, but it needs to be the same from the input perspective, if that makes sense. Once you've decided how many numbers every word is going to represent, you've got to stick to it. You can't change it. I always tell your friend, you don't have to be grammatically correct with AI. That's true, you don't. In fact, very often, it kind of helps when you're not. Smaller dictionary equals smaller model size. Yeah, exactly. You don't need as many parameters in your model if you have a smaller dictionary size, because there's less nuance to learn. Bogateers, you got it. So we need a tokenizer. All right, so def tokenizer. Where's self, comma, we're gonna put self up here. And then we've got our words. And then we have a self dictionary. We need to initialize the dictionary. Should we keep it separate? Maybe we should. Maybe we should have a separate dictionary. So class dictionary. Right? Def init. Self pass for now. And then we could have a tokenizer. Def tokenize. Pass there. Okay. All right. You can ask your LLM to answer like prehistoric guy. All right. You'll see what lemmatization is on an example. Hey, let's do it. All right. Hey, come on, Gemini. Let's go. All right. So let's see. New search here. All right. So lemmatization example. Here we go. And here were BBBBB. Lemmatization is particularly powerful with verbs because it can map irregular conjugations back to their root infinitive. Something simple stemmers can't do. Oh, there we go. All right. That makes more sense. So I understand stemming, which is where you remove the ing and conjugations. This lemmatization is when you convert words to their root word. Okay. It also costs you less. It sure does. It will. You got it. It's so cool. of herself to give out $5 of free AA credits per month. Wow, Loons, really? That's, hey, Bobo Bear, welcome on in. Good to see you. Happy Monday. We're building ourselves a transformer. And that is like a language model, right? You used ChatGPT before, yeah? We're building one. We're building one right now. I like this. I like it. However, things like if you're going to build a language model and you're going to be working with humans, you want to be able to support all of their language as much as possible. And you want it to be efficient all at the same time. Okay. So we've got our dictionary, we've got our transformer. So let's see here. I think we're going to, we do need words, dictionary. We just need the dictionary. I think that's all we need. I think that's it. Pretty sure. I'm pretty sure. I think so. Okay. Even though I don't understand it fully, this is really interesting. Hey, Bogateers! Eventually, it'll click. It will. It'll click after a while. It will. I have uninstalled one and added your own parameters on top. Or are you going from the ground up? Ground up. We did that. We did the other one, Bobo Bear. Yesterday, we did, what do you call it here? Right here. We did fine tuning. We did low rank adaptation fine tuning. We did, and we got it to work. We taught the AI how to do one math problem. That's what we did. And it worked. It worked really well. You can see here the results. You can see the loss is reducing. So you see the number down, all the way down to a number below 0.5. Yeah, and then it actually worked. It gave us the correct answer, which was 1.41 million. We taught it to do the math. It worked. Right here. 1.41 million. Right there, we did it. Have you installed one and added your... Oh, so that's what I did, yeah. So we did both. So today we're going to be doing the PyTorch transformer, which is building our own, basically. So we need a data set. So we got to do items. All right, what are our to-do items here? We got to build dictionary. We need a data set to learn from. Which model did you install? Oh, it was a Quinn. The Quinn model. I think it was from Xiaomi. That's correct. You see there on the subtitles, I got it right. Xiaomi. Okay. Let's see here. So we need, I want my tokenizer to not be here? Okay. I want it to be up here. Okay. Tokenize. So we're going to get our words. Basically our words, a bunch of words. And then we need the entire training data set. So all words. And then we're going to build dictionary and token IDs. So far, so good. Let's see. Then we're going to want self.encoder equals torch.nn.embedding. And I forgot what the parameters are for embedding, so we're going to look that up for real quick. Oh, Quinn is from Alibaba. Oh, right. Mimo is from Xiaomi. Oh, I forgot. Oh, thank you, Loons. I got that wrong. Thank you for correcting me. Look at General on Discord, please. All right. What size? I actually installed Quinn yesterday. This was Quinn 2.5, so it was a little bit older. It was a smaller model. Hey, here we go. Alibaba. Thank you, Loons. You corrected it. Thank you. Appreciate it. Input, output. All right, you guys. What is Novita? Alibaba Novita AI. It's faster. It's more expensive. Novita is great. It's faster and it has more context. Until I saw the price. Until you saw the price. Yep. It's expensive. M-O-N-E-Y. All right, you guys, let's see. Where else are we at now here? Okay. So we've got our encoding, and we need our decoder. Right? Decoder layer. Then we need a linear layer. And what is the embedding? So it's going to be, we need it through number of words. So let's see. Number of words equals len of our dictionary. I do believe this can be a, can we do this? Def len self return self dot dictionary. Did I do self dot words? Yeah, self dot dictionary len. There we go. So that will give us the data that we want for this segment here. We don't need this anymore. We'll just say, oh wait, no, actually this, we could do that. We could just do len like that. That's fine. That works there. Okay. How is it more expensive if you have it on your own software? Oh, well, if you, yeah, okay, so if you're running it locally, then it's going to be free, right? Or if you're running it in the cloud, which you can choose to do, you can run it on other people's hardware, you're going to pay more money for it. This is really straightforward. NVIDIA is an inference provider. They provide models that run on their own infrastructure. The Alibaba is in Alibaba Cloud. Okay. So let me do a quick look up on this really fast. Embedding layer. Here we go. All right. Number of embeddings. Embedding dimension. Okay. So this is going to be number of words. So number of words. And then we need what the dimensionality is going to be. So I'm going to say like 512. Let's do a small. Let's do like 128. Padding, norm, scaled by gradient, sparse, weight, freeze, device, none. Okay, good. Okay. Keep everything else default. And then the output should be this, right? No. It's going to be the other way around. However, 128. Or actually, this needs to be a specific number that's going to be related to our transformer. And this also needs to be a specific number for a transformer. Okay, let's go dims equals 128. So I can reuse that in a few places here. There we go. It's ridiculously cheap. It looks pretty good. That's the price for the new Quinn 3.7 Max, by the way. Okay, good to know. It is a good price, right? That's a really good price. Comparatively. Okay, so I think that's what we want. And then I need to do the transformer self.transformer equals torch.nn.transformer. And I have that reference around here somewhere. Here we go. This is an easy copy paste here. Number of encoding layers. All right, let me copy that real quick. Let's see here, real fast. Here we go. All right. That seems pretty easy to me. So I suppose we could do, we don't need 16 though. I would say we need much less than that. We don't need 12 layers either. So let's do we'll do 4 layers and 4 heads. There we go. This is what the input looks like. So I don't need to worry about that right now. That's going to be our target source. So this part I'm not exactly fully sure on. This part here. However, we're going to figure that part out. Do you know what size the parameter is? Because we may have installed the same one. Oh. I installed... Oh, what are you making? Hey, Abby, good to see you. Welcome on in. We're building a transformer. This is what you use when you talk to like ChatGPT. It's the AI algorithm behind large language models. That's what we're currently working on. We're currently building it. Also, for those of you who are still here, if you haven't heard, we are currently running a hackathon. Join over here in our hackathon channel on Discord. right here. It is a Blocks AI hackathon. Basically, you are building an AI agent and then submitting it. Very nice. Hey, it is very nice. Yeah, I think it's really exciting to me. I like this a lot. Compared to Opus 4.7, it's around 5 times cheaper. That's a good discount. Optimus Prime, to be specific. The one and only. With the Spark, the Transformer. The Transformer! Yep. The leader of... Wait. What are they leading again? Wait. So Optimus is the leader of the Transformers. Not the... Well, the Decepticons are the enemies. What are the other... What's the good side called? Do you guys remember? So how big is the parameters? I don't know. I'm curious about what Loon's got over there. Probably in the range of 30 to 100. I will create Bumblebee Peter Parkour. Yeah, there you go. That's a good one. Autobots. Hey, Resident Alien, thank you. At Resident Alien, thank you. Thank you very much. Opticons. Hey, exactly. What's the hackathon for? This is an AI agent hackathon. You're going to build an AI agent using the Blocks AI framework. It's really easy. Just go to blocksai.com and it's going to guide you. It'll describe all the details. You can connect your agent really easy by copy and pasting this skill file into your code creator, and you can create an agent right there. And it will give you all the instructions on how to run it. Once you're done, it's going to give you a link to the agent. For example, we've got some agents here. We've got a chess agent, and you're going to copy and paste the link that's in your browser and put it over here on Discord. Thank you for the party poppers, you guys. You're going to trademark that. All right, sounds good. Make it a trademark. Mark you the trade. Okay. So far so good. Let's see if this runs. This should run. Go to dimensions, number of heads. We didn't specify the inputs and outputs here, so we're missing something. All right, here we go. Number of embeddings, number of dimensions. Okay, so we need these two things. No, that's the embedding. I need the transformer. Model heads, feed forward. Activation should be GELU. And batch, I want batch first true. All right, let's copy this. So we need to do a couple of things here. All right. So we'll just say dims, keep everything the same. Got number of heads, we're gonna say 4, right? Number of encoding layers, we're gonna say 4 as well. Decoder layers, 4. Feed forward dimensions, so this will just say 512. Although, you know what? We'll keep it the same. We'll keep it dims, so that way everything's easy. Small dropout. Activation is going to be the torch dot GELU. Where's GELU at? Python. I forgot where GELU is. Python. So we need to say. How many locks roughly to achieve a basic predictor? Lines of code. Oh, neural net. It depends on what you're predicting, right? If you're doing a very simple NLP, you could mostly do it in like maybe 5 to 10 lines of code, right? It could be really small. It could be really small, and that's all from scratch, right? If you wanted a more advanced predictor, then you need more lines of code to do more things. So the very basic machine learning model, you can be done in like 5 to 10 lines of code. Everything you see on the screen could be right there. You can see it right there. All right, import torch. Import torch. Torch dot, and then let's see here. Thank you for the hearts, you guys. Dir. I'm looking for rel. There it is, rel right there. Okay. So then where's our GELU? So if I see rel there, do I see GELU? GE. GE. There it is, right there. GELU. Okay. Torch.nn.gelu. Okay. No custom encoder, no decoder. Layer norm EPS. I'm going to leave that default. Batch first needs to be true. Norm first, I keep that the same. Bias true default, and all the rest is good. Okay. So this is going to be our transformer now. There we go. Perfect. Okay. I think that's going to be good here. Let me see if I can run this. Python transformer. No crashes. Good. All right. Decoder only, right? We are going to do... It needs encoder and decoder, right? It needs the encoder and decoder layers. And I do believe we're going to have an... Where... One second. So do we need an extra embedding? I know we need an input embedding. Do we need an output embedding? I think you don't. I don't think we need that. I know there's some reason that I'm forgetting that we need 2 embedding layers. So I'm missing it. I'm missing it for some reason. I don't know where to use this. I forgot. I know you need it. I just forgot where to use it. So let's see if we can get at least a feed forward working here really quick. All right. Def forward. And then we say self, comma, inputs. Basically, let's be words. Okay. This is our plan here. Okay. And then we need to grab our dictionary and we get our tokens. Words, self.dictionary. And do we want to call on the call? No, say tokenize. Tokenize. Yep, tokenize. Here we go. Words. There we go. Okay. We need to do. We need a for loop here. All right. So tokens equals an array, and we can say def normalize. We're gonna not do this one yet, but we will do this later. Normalize self, comma words. We're just going to return words dot. Did you say? Is it lower? Here we go. I think this will do the trick right here. Words dot lower dot replace any non-word character. Wait. We need to do RE. Import regular expression. Okay. So I need to do an RE. Python import RE. RE.sub. And it's going to be anything that's not a word or a number. 0-9 and A to Z. We're replaced with nothing. Like that. Okay. Oh, and then we need the actual value. All right, so hello, this is all one word. Okay, perfect. There we go. That's what I was looking for. Okay. Oh, I thank you for the sparkles. Sergio, appreciated my gratitudes to you. I was just busy coding here. Looks good, gotta go by. All right, Boba Bear, good to have you here. Thank you for the sparkles. Appreciate it. Thank you so much. Sergio, that was really nice of you. Hey, Scarlet Fire Time Loons, yep. I hear it right now. Okay. So we got our, let's do this on our init here. So I've got our self dot, where, do we have an init? We do, right here. Self dot norm equals our regex. And we're going to do self.norm. And we want a space. We want a space here. So we like spaces. Spaces are fine. All right. Dot. Then we're going to return this value here. We're going to say words.toLower. There we go. Okay. So easy normalization. Simple, simple, clean. Easy, easy. Space and maybe a hyphen. Okay, sure, let's add a hyphen. Dash, dash, dash. Can we do backslash dash? There you go. Hyphen. There you go. You asked for it, we added it. We got the hyphen there for you. Okay. Return tokens. Return tokens. And we're going to say for word and words.split. And I need to double check what the split is here. Let's say we've got these words here. Okay, 1 second. All right, we've got the words and we say dot split. Yes, that's exactly it right there. Perfect. Okay. So for word and word, we want to replace that word with the dictionary token, which we have not built the dictionary yet. Wait, parenthesis? Wait, what do you mean parenthesis? We need to build the dictionary. Okay, so all words, so our self.dictionary, dictionary equals, we're gonna do a set, and then we need to grab all the words. We do self.norm on all the words. And we're going to say dot split. There we go. So that's going to generate the dictionary for us. I believe that'll do good, though this won't turn it into a dictionary. This turns it into a set. So let's say self.wordList equals. And then we're going to do some dictionary comprehension here. Thank you for helping me learn Python. Hey, you're welcome, Sergio. Absolutely. We're making our way, you guys. We're building up. We're building ourselves our own transformer. We're doing it right now. All the different pieces that we need. You know what? I bet you there's a way that PyTorch has a mechanism to do this for us automatically. Why are we coding it by hand? We're repeating the thing. We're repeating it. Wait, what? Quinn 3.7 isn't open source? It's not? I thought it was. I thought all of the models that were from the Asia area were open source. I thought they were. I thought they were, you guys. All right, so for x comma y and enumerate, say our self.wordList. Okay, and this is more. So does the index come first or does the word come first? Index. Word. I forgot. Since it's enumerating, I think the index comes first, right? Enumerate. We'll do list. It is. Okay. So the index comes first. You just had a regex flashback lions for lambs. I know, right? Remember when we used to do regex all the time? It was so powerful. We did a lot of Perl, and a lot of regex. At least for now, Quinn 3.7 is only available on Alibaba Cloud and apparently Novita. A little bit of Novita there too. Okay. So we're going to say word colon index. That's it. Easy. Right there. Right there. Doesn't that look weird? I know it looks weird, but yes, this is indeed Python, you guys. This is indeed Python. Okay. I think that will do the trick. So now we've got our dictionary with all the words. We've got our dunder method. We've got our normalize. And we've got our tokenizer. And we need to take our self.dictionary and put the word in there. So that's going to return the token ID. We need to do one thing though. We need to add padding. We have to do a padding. We need to make the very first word the pad. So I need to take all words and type in one word, which is going to be pad. There we go. Pad. Space. Hey, Hashideb, thank you for subscribing. I appreciate it. Thank you for joining in. As you can see here, we're currently coding for a transformer. We're doing all the preparation work with our data. And we're going to then pass it through an embedding, or tokenizer, embedding layer, and then we're going to throw it into a transformer, and we're going to see what the feed forward looks like. That'll be today's plan. I think we can get there. I think we can. I'm pretty confident. So we get our padding here. All right. Hey, looking good to me. All right, no, looks good here. Then we got our, hey, Goose, thank you for subscribing as well. You joined the right channel for software engineering. It's what we do on this channel. We actually write code. We write code with our very own keyboard. We have the AI write code, not very often. Nope, not on this channel. We do our own coding with a keyboard. I know it's outdated. I know, you're right. It's out. You're like, wait a second, Steven. Don't we use the AIs to auto-generate the code for us? I know, right? It's like the evolution from punch card to keyboard. It's that much. And it's expected now. Everyone who's typing code anymore. We are. We are. Okay. Thank you for subscribing. I appreciate it. All right. So I do believe we've got our dictionary. Looks good to me. We included the padding. We've got our length, a normalizer, and our tokenizer. So we should be able to, let's see, I think what I'm going to do is I'm only going to use this as our training data here. So we got our training data here. We're going to say training data equals. There we go. And we'll have more training data. Don't get me wrong. That's like 5 words. 5 words is not enough words. It's not enough words. You're downloading QuinPaw, and their CDN is so bad, it's faster to connect to a Japan VPN to download it. Whoa! Dang. That is pretty slow. The whole point of CDN is to make it fast, so data is near you. You're assuming self-attention lines for lambs. You got it. Self-attention. That's what we're doing here. And right now we are going to be using the easy approach. We'll build this late. We'll build it from scratch later. Right now, there's a class that's already pre-written for us that allows us to specify all of our parameters directly, including our own activation, which we're going to use GelU. And we're going to be using transformer. So I'm missing a few things here. However, I think we are on the right track so far. In France, you got a 500 kilobytes per second. Well, that's half a megabyte a second. So that's going to be really slow to download some AI models, right? That's really slow. Okay. Python transformer. Line 20. Go. There we go. It's so syntax is working, you guys. And with the VPN, you got 7 megas a second. That is a lot faster. That's 14 times faster. 14 times faster, Linz. All right, let's keep going. Okay. So let us do a feed forward and get our tokenizer and return tokens. Let's try it out. Model equals transformer. And do we need a dictionary? We do, so we need to initialize the dictionary first. Dictionary equals dictionary, and we pass in training data. Dictionary. See if it works. See if it made. Hey, working so far, so good. It's not the model, it's the app. Oh, okay. Since it's an Electron app, it's still a gig. Okay, got it. Those Electron apps are going to be... It's got all the Chrome. It's all the Chrome is baked in there. Hey, Siva! Thank you for subscribing. Welcome on in. You joined the right channel for software engineering. We're really typing. As you can see here on the screen, we're building a transformer. Self-attention, right? As all you need, self-attention. Got their attention. All right, so model forward training data. Let's see. Our output should be a bunch of tokens, right? A bunch of numbers. Print output. We got through part of our way here. Where's the architecture at? Here. Oh, here we go. Here we go. How far are we to the process? We're right here. We're right here. We're at the very beginning. We're still at the beginning. No, there's a lot of code involved, right? For a transformer. We're only going to get the IDs right now. So I believe, yes, just the tokens. Here we go. Did we do it? Oh, got an error. Did I type it wrong? Oh, dictionary. Where are we here? Oh, we should say self.dictionary equals dictionary. Okay, there we go. So we have that around, so we can keep it for later. All right, and then we say, oh wait, see, can we do dims equals? I think we can do that, right? We can do that in Python. We can do multi-variable assignment. You post something on general Discord. Is this true? Let's find out. General. From encoders to decoders, early models, original transformers, BERT, use bidirectional encoder representation, used an encoder-decoder setup. The encoder reads the entire input to create representations. The decoder produces the outputs. This made them great for specialized tasks like classifying or translation. Latest models, GPT series, almost universally transition to the decoder-only architecture. By dropping the encoder, the model acts purely as an autoregressive text predictor, making them highly adaptable to zero-shot prompting, coding, and open-ended conversation. Interesting. Interesting. Well, you need some sort of encoding. So there's obviously going to be an embedding, and that still happens, right? So look at memes. Okay. It still happens. This is giving me nightmares. Oh, is this some AI here? We got some AI? Yeah, that's some AI right there. Okay. A little bit of AI. Yep. Uncanny Valley. I'm just learning about it, so I don't know. So yeah, so there's gonna be some sort of encoding. Loons, this is scary. I'm concerned. I'm concerned. Isn't BERT encoder only? Yep. So BERT acronym, bidirectional encoder representation for transformers. It sounds like encoder only to me. It does, right? Encoder only. See, I typed it wrong. It's gonna know. Yes, BERT is encoder only. You figured it out. Yes. Thumbs up. You're right, Jens. Hey, Gustavo, thank you for clicking the hi button. Welcome on in. Good to have you here. All right, I want to go back here real quick. Okay, Python. I want to check out, I was thinking of something and I need to remember what it was. The output, where was it? I'm missing a part. Where was it? That's why I was questioning it. Yeah, see, like, it's weird because you still need some sort of encoding part, right? Especially here. It is called embedding, but there's still a tokenizer and an embedding. And essentially, you've got, after that, the filters or the projections. So this is still encoding. What counts as encoding to me is converting raw data into numerical representation that the AI can understand, as far as I know. Is there something different, though? That was an AI response to a question I asked? All right, so let's see here. Jiminy, all right. What is encoder in AI? Here's the thing. AI has all these fancy terms. It does. It has a lot of fancy terms. You're right. You've got like, what's an encoder? What's a vector? What's a matrix? What is all this autoregressive stuff? What is NLP, natural language processing? Input, encode the receiving data, English. See? It's exactly what I thought. The encoder receives data, the English sentence. The cat sat on the mat. Processing through the layers of the neural network like transformers. It analyzes how words related to one another. For example, it learns that sat refers to cat. Okay. Output context vector. Outputs the fixed size of the matrix. The encoder receives the original data and it needs to transform it into numbers. Encoders are often paired with decoders. Takes the concept vector and uncompresses it into a format like translating into French or generating an image description. Input data, encoder, right there. See? Context, decoder, output. So there's still got to be some sort of encoding. Right? It's like walking on a thin ice to run the video from the Discord on YouTube. Oh, I know, right? Yeah, I know. I could have clicked that and it could have been dangerous. I trust loons, though. I trust loons. It is. It's like thin ice. You're like, whoa, whoa, be careful. Be careful. I need to, like, remember that. Thank you for mentioning it. Okay. Decoding seems powerful. Yeah, decoding is just taking the numbers and converting them into the representation of whatever your output's going to be, I think. Right? The decoding site. So, right? Decoding output data. Right there. Decoder. Translation. Tokenizers. All right, we're almost done. We're almost done. All right, so I want to... What was I doing? Let me run that again real quick. Transformer. Something's broken. Oh, number of words. Right. Okay. We changed that to self, so we need to change that over here. I need to do number of words self. Oh, right. Python. All right. A equals B equals 0. A, B. Cool. Say number of words equals number of words. There we go. So we are not doing the multi-headed attention layers. We are focusing on the attention mechanism in this like. Hey, Gustavo, in this live. Yeah, so this time around, we're going to just use the multi-headed attention is going to be there, right? So we've got 4 heads. And the attention layer, everything is going to be calculated for us in this nicely pre-written PyTorch class. We're going to start with that first. Once we get that working, we will implement this layer ourselves from scratch. That'll be the next. We won't do that today. We'll do this in future streams later this week. So for now, I just want to see what a feed forward looks like to make sure that we're getting all the right data. The output dimensions are going to be important so that way I can understand what the next layer is going to look like. Oh, and one line is actually good. Yeah, exactly. One line right here. Let me make it easier to see all the parameters we're currently using. There we go. Whoop. F space. There we go. Okay. So here, this is what our transformer looks like. So we got our dimensions, 128, number of heads, number of encoder decoder layers. See, we got them right there. Feed forward dimensions, drop out, activation. We're going to use GELU instead of ReLU because I like it better. Batch first. Because when you do ReLU, you can lose data. I feel like it's it throws data away. And I feel like we have an opportunity to keep some of it. You get to keep a little bit more with GELU. Okay. So let's see if that Python works there. Okay, for word and words. Hello. Oh, whoops. Okay, 1 second. Forward words. Oh, right. We have to tokenize that. So, we need to normalize self.dictionary .norm normalize words. There we go. So we have norm equals norm. There we go. That should do the trick there. Okay. What about leaky ReLU? Hey, there we go. Leaky ReLU. Yeah. That's a good one. That's also a good one because it won't turn everything to 0. With leaky ReLU, it has just a little bit of it, like it's a scale, right? It keeps the number, it just doesn't turn it all the way 0. How's it going there? Parzival. Hey, Parzival, good to see you. Thank you for clicking the hi button. Welcome on in. We're building ourselves a transformer. What makes ReLU better in this case? And Gustavo, I don't know. I thought leaky ReLU and ReLU were basically the same. There's definitely a difference. Let's see if we can ask here. Jiminy, we'll go ReLU versus ReLU. Oh, wait, no. Wait. No. Wait, new chat. Leaky ReLU versus ReLU. That's what we want. Casual Monday activities, Percival. Yes, exactly. Leaky ReLU is a deterministic, precise linear function. Has a sharp, non-differentiable kink at 0. ReLU is a smooth, non-monotonic function. Let's see. Okay. Probability of being activated, creating a smooth curve where negative values can drop slightly below 0 before tapering off. Oh. So it doesn't go all the way to 0? It only goes most of the way to 0. Yeah, we keep the information instead of getting rid of it because we might need it. All right, I might need it. I want that. I want it. I want the data. I don't want to just drop it. I don't want to just throw it away. So, right, we get the max, which is ReLU, or X. See, some sort of like, what is this? Like alpha times X, which is going to be a fraction. So we shrink it, right? We shrink it down. Or X, whichever's bigger. Okay. With ReLU. Oh, wow. Okay. Let's see here. If X is not 0 to 1, where X equals... If X is less than X, I don't know what capital X is. Here, let's do this. Obviously, ReLU is going to be more computationally expensive, right? So, shape compute cost. Extremely low, moderate, requires approximation. So yeah, ReLU is going to be almost free, nearly free. Moderate ReLU, so compute cost a little bit higher. ReLU isn't kinky, got it. Hey, Kyle, yeah, exactly. There's no kink. No sharp kink. Smooth curve, non-monotonic. Tapering to 0. Constant. Not at x0 though. It's not differentiable when x is 0. I prefer smooth curves. Yes, there we go. I like my AI models to have smooth. It's gonna be smooth. Because if you got all these like spikes all over the place, you can't easily create a generalization. You've done some sort of weird overfitting at that point. Okay. So, we got our tokens. We did it! We got the tokens right there! Alright, so far so good. Right there. Alright, now let's run it through the feed forward real quick and see if it works. Let's see if we can get it to work here. Alright, so we need our embedding. Let's do our embedding layer first. So self.encoder. So encoder embedding. I'm just going to say encoder. All right, so self.encoder tokens. That should automatically get me the embedding. Embedding equals embedding. Okay, let's return our embedding. And this should be a 2D matrix with a bunch of numbers in it. Or completely fails. Or completely fails. Can we see a graph? Yes, that's a good idea. We should. I actually really wanted to do that. All right, so ReLU graph. In a leaky ReLU, I know what that looks like. It's linear, and then it has, like, it tapers down, like a real tiny. Here, I'll draw it. I'll draw the leaky ReLU. So it's actually pretty easy. So here's a chart, right? Here, think that's a line. That's the x-axis, and then we have, this is 0, And then at 0, it kind of goes like this. So that is a leaky rel U. This is leaky rel U. Now a gel U, I don't know what that looks like. So before I do this, so let's do a leaky rel U chart. Ah, see? I told you. Wait. Yep, see right there. Zoom in. Ah, I got it pretty close, right? I got pretty close. The I can save the world. Hey, Krishnap, thank you for saying it. Good to have you here. Happy Monday. We're currently doing some AI stuff, if you didn't notice. If you didn't notice, there's evaluate. I thought you wanted to use encode. There's evaluate. Yes, encode, that might be it. That might have been the problem that we had in code. At this point, I don't need university. Hey, Gustavo, you really don't. All the information available for you for free on the internet. University. You can even go to Harvard, MIT, and Stanford on their website. They have the courses fully recorded and free, right? If you wanted to pretend to go to college, there's the MIT videos, OpenCourseWare, all courses right there. Like you want to learn some physics, classical mechanics, right here you can download the course. And they've got everything. Week introduction. Oh, you want the videos? There they are. All the videos. Isn't that great? Isn't that great? What's up? What are we doing here? Hey, how's it going there, Lupad? Lupad, good to see you. Welcome on in. Happy Monday. We're currently learning about transformers. You know, the thing that you do when you talk to ChatGPT. Right? We're making it our own. All right, so I want a gel U chart. Ah, look at that. Wait. Here we go. That is interesting. So it's got a little smooth bump right there. Look at that. It's got a smooth bump right there. However, it goes to 0, which I don't know if I like as much. I don't know. I think leaky rel U might be better. I think I might like leaky rel U better. Because it's got a little bump there at the 0. That's a nice curve right there. It's a good curve and it's suggestive. I think it's kind of representative of things that we recognize as humans. I'm being vague on purpose. Okay. Encode. Yep. There you go. You called it. You called it. Thank you very much. Thank you for finding the error. 0 is good, smooth. Peter Parkour, I think 0 is pretty good. It works. What? Wait. Yeah, because it compresses the negative values. Oh, yeah, it does. Okay, got it. So it gives you a little bit of negative, but only just a little bit. Just a smidgen. Thank you for the reactions, you guys. Appreciate it. All right, so we should see a 2D. Oh, just kidding. It's called encoder. Encoder. There we go. Got to spell correctly. All right, so we are missing something. Number of words. What is the challenge? Why is our encoder not happy about this? Let's see, embedding argument indices must be tensor, not a list. Must be a tensor. Wait. Hold on. Wait. Embedding argument indices position 2 must be a tensor. Oh! Of course. Of course, you guys. All right, here. I forgot to do this. Torch.tensor. Done. All right, good to go. Oh, now we got a different error. Okay, expect tensor for argument 1 indices to have one of the following scalar types long. Oh, right. Okay. D type equals torch.long. Let me do that. Is it like that? Hold on, Python, import torch, import a torch.long. No. How about we say, see, it is, so dir torch. Let's look for ONG maybe. Let's look for ONG, question mark, ONG. Long, oh, it's just lowercase long, okay. How about that? Okay. Torch.long. in 64. That's it right there. All right, did we get it? We got past that one. Now we're on a new phase. What is our feed forward? Let me just hide this really quick and we will return tokens. Just to make sure that we are in the right spot. Tokens, there we go. Ah, see, I knew it, Okay. Torch.long, it didn't like that. New received invalid combination. It's the D-type. Tensor D-type right there. That's fine, What did I do wrong? Hey, let's go in there, SSH. Hey, your name, I like your name, Secure Shell. Yo, hey bro, how are you doing? Oh, I missed your message, whatever you said. I didn't see what you said because you got moderated. Good to have you here. Welcome on in. Happy Monday. We're building a transformer. Why don't like it? I want it to be a torch type long. It's got to be a type long. Is that not good enough? It's right there. It's long. It's a type of long. Right? All right. So let me see why it's not happy with that. Let's see. Wrongly return 2 from forward. Wrongly returning 2 from forward. Oh yeah, no worries about that. Don't worry. I did that on purpose. Don't worry, it's temporary. It's temporary. Thank you for paying attention though, Peter Parker. Thank you. Peter Parker. Okay, I want to that D type. Oh, torch. Maybe do we? Let's see. Hold on. Python torch.d import torch torch.d type. Is that a thing? It is. .long. No. Okay. Torch dir. Let's do dir on this. There we go. There's nothing there. I already had it the right way. I already had it right. Steven CTO robot dance meme win. Oh, maybe someday I have to practice it. What are the secret of your energy, bro? SSH, thank you for asking. I eat healthy. If you eat healthy, then your body is able to hold on food and have a continuous amount of energy throughout the day. If you eat animal products or refined food, all of your body will get bogged down by the animal products because it takes a lot of energy for your body to break down the animal product, and there's a lot of byproducts that your body has to deal with. So you waste a lot of energy by eating animal products. It's necessary in certain cases when you need to survive off of calories. However, you're going to lose most of your energy if you eat animal product. Number 2, if you eat a refined product, you're going to get a giant spike of energy. All that food that you eat is going to get absorbed and converted to energy instantaneously in your body, like within 10 or 20 minutes. So you won't have a long sustained run of energy. It's all about what you eat. So if you eat whole foods, vegetables, like broccoli, cauliflower, tomatoes, berries, fruit, and then you eat beans and grains, berries and seeds, all that takes a long time for your body to break down without expelling a ton of energy to do it. So you no longer need to drink coffee. You don't need any caffeine anymore. If you just eat healthy, you're good to go. You thought so? It's different? It's not. Oh, I eat an animal product. I'm being healthy. Nope. Oh, I eat Oreos. I'm being vegan. Yes, you are being vegan at that point, but you're eating Oreos. So you're a vegan. Yeah, I eat the vegetables. Exactly, Ola. You know it. Ola kun lene. Exactly. Eat the vegetables. It's better for you. Your body wants it. You're happy. You eat meat, not gonna lie. It's Steven. Sorry, bro. It tastes good though, right? It tastes really good. It's a treat. It tastes really good. It has consequences. It's called optional illnesses. Wait, elective illness. You are electing to future illness and present illness. You're buying your future today and selling. You're selling out. I don't know what to say. You're trading. You're trading happiness today for sadness tomorrow, maybe? Okay. All right, so I want long, though. I want long, right? Question mark ONG. Long tensor. Is that it? Huh. Okay. Very rarely drink alcohol. Oh yeah, that's a refined product, right? So that would be a problem. Like once or twice a year, special occasions. Hey, very nice. All right, so that's a good step forward. Hey, Michael, good to see you. Welcome on in. Happy Monday. You and me. Oh, wait. I should give that a go because I'm sleepy all the time, even though I drink a lot of coffee, right? Yeah. It's because your body is getting all the spikes of energy, or you're getting bogged down by meat because your body it takes a lot of energy to process the meat or animal products like milk, dairy, eggs, things like that. And that is going to take away from your energy throughout the day. So if you eat like Brian Johnson does, he only eats seeds, beans, whole vegetables. He eats some fruits like berries. He eats a lot of berries. And that's it. Beans, greens, berries, and seeds. You're good to go at that point. You also don't want to get them processed. So you just eat them whole. That's another thing. Because you want your body to be able to have that energy. Because you've got a very big digestive system. And you want to use it all. Chocolate. Hey, chocolate. We don't eat eggs. Daughter's allergies. Ooh, yeah, danger. Danger zone. Those eggs. Yep. That's also an animal product. Oh, I'm being healthy by eating eggs. Nope. Sorry, you're not. You thought you were. You're being healthier than eating maybe some other things. So that's still a step up. He eats chocolate. Chocolate's very tasty, isn't it? All right. That was a fun rant. I am out of water. And I before we head out here, because we're going to wrap up here, before we head out, I'm going to make sure that we get a feed forward working. So the only problem is that my embedding layer is incorrectly initializing. How do we do this? Python transformer. See, received an invalid combination of arguments, but expected device. Well, how else do I initialize the tensor? How do I initialize the tensor to be of a certain data type? Right? And it already was a long data type. So what's the problem? Let me see here. All right, let's try this again. Steven, you should show your blood work. It's pretty good. Oh, see, see? It's not a long. It's a float. Hold on. Let's go to the docs, yeah? All right, torch.tensor. All right. Type. Yeah, right there. D-type. I told you. A multidimensional matrix containing the element of a single type. Please see torch D-type for a more detailed... Okay. How do I specify the type? Right there. D-type. Torch int32. Okay. So how about we say int64 then? Torch. Oh. Let's see. So that's when it's generating. Maybe we say .2. I've got an idea. .2. Torch.long. How about we do that? I think that might work there. Do you lift or run, etc.? Steven, you should... so I don't, and I probably should. I should probably do some muscle building. The thing is, though, I'm trying to gain weight, and I have trouble eating enough food in order to gain weight. So, I'm working on it. Once I get that down, then I will start doing maybe a little bit of exercise, right? A little bit. So now I should have the correct there we go. That's what I want. That's right. Right there, you guys. Right there. Okay. So now our embedding should work successfully. Let's try this. Are we on the right track? I think we might be. Let's see. There we go. All right. We did it. So now that we got our embedding, Let's throw it into our transformer. I think we're ready. And if we do this, we've completed today's task. That's it. I'm taking you to the gym. I know, right? I should go to the gym or something. I should. I need to gain some muscle weight. All right, so let's do the out equals self.transformer. Transformer, thank you. Embedding. Now the thing is, there is extra things are needed, and I don't know this. We might need to learn more about this. So return out. Okay. This is not enough. We need to pass in more variables. I don't know specifically, like source target. Like, I don't know what that's going to be. What I could do is just do tokens. We should do that. So I think I should get an error here. Missing one required argument, target. Okay. So let's just do embedding. We did it. The only thing is, I don't know what this is supposed to be. I don't know what this is actually supposed to be. To do what this is. What is TGT? Is it the next word? Every tech billionaire eventually hits their glow up, Steven. It's inevitable. Oh, right, yeah. Like how, what was it? Yeah, the Zuckerberg and the Bezos, they got swole. Right? They swolled up. You're on your way. Hey, we're trying. We're trying to make our way. All right, so this is a to-do for tomorrow. I think the attention score. The attention score for the target. We also need a mask. So let's see. Let's add to do. Oh, actually, we don't need to worry about the mask right now because I think the transformer automatically did that for us. Consider mask. See, we also need to get the TGT, the second param in transformer. 1, 2. Or the QKV. Oh, right. So the QKV is going to be identical. They're the same inputs. There's also a QKV layer, which are going to be the projections, the filters. If you're familiar with convolutional neural networks, they're the same. And then after you pass them through the projections, you're going to do the self-attention. The good news is this does all that for us automatically. So what I need to understand is what this is going to be. Is this our target output? Will this be the next word? I think it is. I think it's the next word, right? I'm pretty sure. So here's all of our words. And then, yeah. So I think that's the plan for tomorrow. Okay. Get status. It's not a repo. Get init. Get add. Get status. Get, wait. Thanks for your time and sharing your skills. Hey, Brad Jackson, Chord Life, absolutely. You're welcome. We'll be back tomorrow. We're going to wrap up today. We'll be back tomorrow with more transformer. We're going to get the built-in transformer to work successfully and do a feed forward, do optimization and training on it. And then once we find success there, we will take our existing code and rewrite this entire layer here. We'll rewrite this all from scratch. So we'll do QKV, all from scratch. Thanks, Stephen Peter Parkour. Thank you. It's always sunny in Philadelphia. Stephen gets buffed. We could, right? That would be a lot of fun. Maybe someday we do that. Maybe someday we turn into Brian Johnson. I don't know. Do I really want that? I don't know. But it was good to have you guys all here. Z Transformer is stronger than you. The good old Z. Chi Brimmered. Hey, thank you. All right, you guys. Had a good fun day today. Got a lot done. We'll be back tomorrow. Had a good one. All right, everybody. Have a good one. School stream, Steven. Excited for tomorrow. Have a good day, everyone. See ya. See ya, everybody. See you tomorrow. Bye, everybody. Good to have you here.